So now we've come to the final goal, what we're after. What we're after is a solution to the second order linear differential equation, which we can write by inspection from the transfer function. In other words, given this, we would like to be able to write the cosine function, shown down here, from a pulse input, because we know that the transfer function is actually the inverse Laplace transform of the transfer function is the response to an impulse. So if I give an impulse to this system, the response will be given by this cosine function, and we want to be able to have a graphical shortcut to evaluate that right away. So here's a case where we have 32 over s squared plus 2.4s plus 16. And the first thing I do is to put the roots. So I'll take 1/2 of that, that's 1.2. And I know my real root is minus 1.2. It's minus 1/2 of the coefficient of s. So my real root is located minus 1.2. This is omega n squared after that at 16. So my omega n is going to be equal to 4. So line at minus 1.2 where it intersects 4 is going to be the location of my root. And by the Pythagorean theorem, then I can find my omega d equal to 3.8 radians per second. My system is going to oscillate at 3.8 radians per second. Now the pulse response, if I give a pulse, I need to solve for the first residue. So my first residue is shown here. I have to carry the gain of 32, which was given to me. But then I know from the many times we've worked so far that the only pole I have is here, its sister pole. So I'm going to have 2 omega d in the denominator at an angle of 90 degrees, which will become, the angle will go to the numerator as minus 90 degrees. Therefore, my pulse solution will be, again, I'm carrying my gain with, I also have to do that, but the residue then will be twice the residue, and twice the residue is just going to give me 1 over 3.8, so there's the 3.8, and the angle of the residue is going to get attached to the frequency, and the omega d is 3.8 t, and then the sigma is going to give me the envelope of the time response. So in time, a pulse input will give me an envelope, and that envelope looks like a first order decaying time response. The envelope will have a time constant of 1 over zeta omega n, which is going to be 1 over 1.2, and that's going to be how fast the envelope decays. Inside that envelope, the system will oscillate at 3.8 radians per second, and it'll be a phase loss. There'll be a phase loss at the start of it, so it'll actually start out at a different value. Phase loss will come from this 90 degrees here. So we can see that if this pole moves up like so, then the frequency will increase. If the pole moves out like so, to the left, then the real part will increase negatively and the envelope will decay faster. If the poles move apart, then the residue of the pole will decrease, because we're looking at the line drawn like so. So if the poles move apart, then the residue, or this number in the denominator, will increase and reduce the magnitude of that pole. This kind of gives you an idea of how this stuff works. So as a test to see if you understand, what would the response be for a step input instead of a pulse? Well, how would I solve that? Well, I know a step input basically is going to add a pole at the origin, like so. So if I wanted the response to a step input, then my residue that I'm going to evaluate at the first pole, the residue is going to be equal to 2 phasors. I'm going to have one phasor from its sister pole that we've been doing all along at P star. That's this guy. And then I'm going to have another pole drawn from the origin. And that'll be a pole, we'll call that LP0, since it comes from the origin. And the LP, of course, is going to be equal to what? 2 omega d j, right? And the LP0 from the origin is going to be equal to 4 at an angle of what? Well, the angle looks like it's the arctangent of 3.8 over 1.2, right? 3.8 over 1.2 put into the correct quadrant. So it's going to have an angle, and I'm just going to call that the angle of LP0, like so. Therefore, the sinusoid y for a step will equal twice that residue, and twice the residue we have already seen. We have 32 over 3.8. That takes care of that one. But now I'm going to also divide by 4. The real part of the root stays the same. The omega d stays the same at 3.8. But now the residue is going to be equal to what? Minus 90 degrees minus the angle of LP0. And the angle of LP0, of course, is this angle measured from the real axis to there. So you see that I have another phase loss. There's going to be an increased negative phase in the step response that I didn't have in the pulse. Now, I'm not going to do this, but suppose I wanted to increase. I wanted to get rid of at least 90 degrees of phase. How could I get rid of 90 degrees of phase loss in my angle over here? Well, how about putting a 0 right there? If I put a 0 right there, then this, when I evaluated my residue, I'd have an LZ in the numerator. And an LZ would add 90 degrees, right? And by its length would be 3.8, and that would cancel out this guy, and it would cancel out this guy. So you can see the power of this method, because by moving poles and zeros around, and that's what we're going to be doing when we're building systems, we're going to put poles and zeros into the system, and we can then visualize how we're increasing and decreasing the phase of our cosine functions and increasing and decreasing the magnitude of the response as measured by this constant in front. Hopefully now you're more familiar with complex numbers, how they relate to Laplace. And we're going to be using this technique extensively, so I hope your time on this is well worth it.